So in this example, we have two parallel frictionless rails that are conducting, and they're connected in two places. On the left side, by a conducting wire with a resistor in it, and on the right side, by this movable, let's say, gold-colored conducting rod that's able to slide along both connection points. Okay, so there's a magnetic field inside these rails, as shown, and in part A, we want to find the magnitude of the force directed to the right such that we can move this, well, a conducting bar at a constant 2 meters per second. Okay, so what should clue you in as to what to do in the first place is, well, there's a constant speed, right? Constant speed. That should clue you into the forces should cancel. We only have one force shown, that's the force applied. Well, there must be another force, and if the force is canceled, that means that force has to be to the left. And what force is that? Well, if we have currents and magnetic fields, we have a magnetic force, FB. Okay? So, in addition to that, there's a magnetic flux. Right? This kind of loop here has some cross-sectional area and will be changing in time. Specifically, it'll be increasing if that bar is pulled to the right. So we have an EMF as a result. Okay, so we can write that EMF like that. And that will be increasing, and you can think of an EMF as a voltage source, right? It is a source of a current for a given resistance. So this is also I times R. That's the same as Ohm's law, way back in, I think, chapter 26. Okay? So this is Faraday's law and Lenz's law in coordination with Ohm's law. Okay? Now, for part A, we want to find the force. Well, we have both of them. Let's set them equal to each other and see what happens. So let's see. In order to do this, we need a positive direction. Let's see. I put right positive. We have then the applied force F minus FB equals 0. Right? And so thus the two forces are equal. What's the magnetic force? It's QV cross B. Right? Let me write that over here. Remember, QV cross B. Well, do we know the speed at which these charges are moving? Not necessarily, right? We're not given that. Another way to write this magnetic force, remember, is IL cross B, right? The current times the distance crossed with the magnetic field direction, okay? We do know a distance L, and we can find a current value, right? Or a current magnitude, I should say. So let's use this second variation, and I'm actually going to write the magnitude of that. And what's the angle between L and B in this case? Well, L, we can say these charges are going up or down, right? Up or down. And the magnetic field is going into the page, okay? So that means that direction or that angle in between is 90, and the sine of 90 is 1. Okay, so now we have simply ILB. And we need a way to find the current now, because we don't have that specified. L and B are specified, but we need current. Luckily, we're in chapter 30, and we can do that using Faraday's law. Right? So the EMF is negative the magnetic flux per time. So if the flux is increasing, we need the induced current such that the induced magnetic field will effectively want to decrease the flux. Okay, let me say that again. Because this magnetic flux in here is increasing, the induced magnetic field will want to decrease it again. So because this field here shown is into the page, right? That's what the X's mean. We need the induced field to be out of the page to decrease it. So let's write that B induced needs to be out of the page. And using the right-hand rule, if you put your fingers inside this area in the direction of that induced magnetic field, they should be pointing up towards you. And your thumb means that the induced current is going that direction. Right? And that's the current right there. Right? That's the same current. And so we need to find or evaluate the change in magnetic flux. So let's see. The magnetic field magnitude, that's not changing, so let me bring that out front. Now we have the integral of dA. Okay. I guess I should put cosine of 0. That's 1. What's the integral of dA? Well, the area right here is simply length times width, right? Or base times height. What's the base? Well, we know one is L, and the other direction is this one. Because that's changing, and we've specified the x-axis, we might as well just say that's x. So let's see here. d dt of Lx. The only one of those that's changing is x, and so we have negative BL dx dt, which is the same thing as v. The velocity at which that bar is being pulled, right? Which is the 2 meters per second. And so this equals this equals I times R, and now we can find an expression for current. Minus BLV over R. And this is what we plug into our force equation. Right there. All right? To give us the force applied is, actually we want the magnitude. So magnitude is BLV over R times LB. Right? Plug that into right there. And so that means B squared L squared times V over R. What do we have? B is 2.5. L is 1.2. The velocity is, or rather speed I should say, is 2. And the resistance is 6. And this should give us a value of 3 newtons, if I've done my math correctly, for the magnitude of that force. Okay? So that's part A. We're effectively equating forces to move at a constant speed. And because the magnetic flux is increasing, that induces a current to try and get that flux to decrease. Right? And so that's why the induced current travels in this counterclockwise direction. Okay? So we used Faraday's law in conjunction with Ohm's law to figure that out. That was all part A. Right? Part B, much simpler. Part B is at what rate is the energy delivered to the resistor. So there's a current flowing there's a current flowing, we'll say downwards, right, across that resistor. We're basically finding power, right? That's the rate of energy dissipated or delivered. So let's go over here now for part B. We're basically finding power. So power in relation to current is I squared times R, since we know the resistance. Let's see. The expression for I we found was BLV over R. Sorry, minus BLV over R. We'll see the minus sign, doesn't matter. All that squared times R. And so the negatives cancel. We have B squared, L squared, V squared, all over one term of R. And if we plug in the values, 2.5 times L was 1.2, oops, squared. The velocity was 2 again, divided by the resistance of 6. This should give us a value of 6 watts. That's a unit for power. Okay. This is also the rate at which energy is dissipated to the resistor, which is the same as the heat generated to the environment, right? And that's purely coming from the fact that the magnetic flux is increasing. Okay. So that's the example for emotional EMF. Thanks for watching.